Good morning, everyone. Today we're doing Unit 5, Lesson 2, Transformations of Sinusoidal Functions. So the next two lessons are going to be about different types of transformations of the sine and cosine curve. Today we're just going to look at translations. So translations, remember from years past, translations is just another word for a slide. So that means we're going to slide our function up or down, as well as left or right. So those are the types of transformations we're going to look at today, just moving them in one direction or the other. So the first thing we're going to do is we're going to look at the base function of sine. So I would like us to fill out this table of values. So we're going to calculate y equals the sine of theta to determine the 5 key points. We're just going to fill out this table of values for now, and then we'll talk about what our key points are. So if I was to plug this into my calculator, and maybe you remember some of them, but for now we just need it to the decimal. So if I plugged in the sine of 0, that's going to equal 0. The sine of 45 is 0.7071. Okay, pause the video and go ahead and fill out the rest of that table of values. So here is the rest of the table of values all filled out. We're going to go ahead and plot those points on our axis. So our theta, or our degrees, is on our x-axis, and then the sine of theta is on our y-axis when we're graphing these, don't forget. So when theta is 0, y is 0. When theta is 45, which would be somewhere between the 30 and 60, then our y value is 0.7071, so something like that. When theta is 90, then our y value is 1. Okay, at 135, we're back down to that 0.707. Okay, I'm just going to plot the rest of these points. So 225, we're dipping down below the x-axis. Same with 270, we're at -1. 315. Hopefully you can see a pattern that's occurring here, and then at 360, we're back up to 0. Okay, so if I connect these, we did look at the sine curve in yesterday's notes, so we should start to become familiar with the general shape of the sine curve. Okay, I want to talk about the key points of our sine curve because that's going to help us as we continue forward with our transformation. So our key points are going to be whenever there's a turning point. So our turning points, remember, are at a maximum or at a minimum. Another key point for a sine curve, so let's highlight our maximum and our minimum. Those are our key points. Our other key points are at our axis. Okay, because that axis is the center of the graph, and the graph ultimately always comes back there. So it goes from our sine curve goes from our axis up to our max, back down to our axis, down to our minimum, and back up to our axis. I just want to write that our key points are our maximum, our minimum, and our axis. And I want to label where those key points are on my table of values. So on my table of values, I have my axis is at 0 for the sine curve, right? So anytime my y value is a 0, then that is a key point. So it's 0 at 0, 180, and that's 360. So you can see that in one period, the sine curve touches the axis 2 times, all right? And then we're also going to identify where the maximum and minimum are. So our maximum value is when sine of theta equals 1, and our minimum value is when sine of theta equals -1, which is at 270 degrees. Okay, so those are your key points, and we're always going to be trying to use those key points whenever we're doing transformations to slide or stretch or compress the function. So let's take a look at our first transformation. So we're going to make a table of values and then graph the following to compare to our y equals sine of theta. So you can see here that all I have this time, instead of having all of those thetas, I'm just going to evaluate my key points, and any transformations that happen to the function, we're just going to perform on those key points. So I know my key points. My axis is at 0 degrees, at 180 degrees, and at 360. So we should start to become familiar with what are our key points for sine. And then we have a maximum at 1, and we have a minimum at 270, which is -1. Okay. So now for the next function here, y equals the sine of theta plus 3, we're basically adding 3 every time we calculate our sine of theta. So I found that the sine of theta for 0 was 0, and I'm going to add 3 to that. So now y equals 3. Okay, for the sine of 90, that was 1. I'm going to add 3 to that, so you get 4. Okay, and so on. Negative 1 plus 3 is going to be 2, and 0 plus 3 is going to equal 3 again. So we're going to plot these points. Okay, so now my x values haven't changed. My x values are still, or my theta values are still 0, 90, 180, 270, and 360, but my y values have increased. So let's plot those points. So now at 0, my y value is going to be 3. At 90, my y value is 4. At 180, I go back down to 3. And at 270 now, I'm down to 2. And at 360, back up to that 3. Okay, if we connect this, hopefully we can see that what's happened to our critical points, okay? So now we have a maximum at 4. We have a minimum at 2. And our axis, we draw that horizontal line that cuts the graph in half, is at 3. So this is our axis, right? So when we added 3 to the function, we can see that basically all of our y values increased by 3. Okay, let's see what happens if we were to subtract 2 from our function. I think you guys probably see where this is going. So if I did, again, for the sine of theta, so the sine of 0, once again, was 0. I'm going to subtract 2 from that. All right, and then it was sine of 90 was 1 minus 2. All right, and we're going to continue on in that fashion. Okay, so those are the points you should get when you subtract 2. So let's plot those points, see where our maximum, our minimum, and our axis are going to fall. Okay, so at 0 now, I'm going to plot a point at negative 2, then at 90, at negative 1, at 180, back down to that negative 2, 270, we're going all the way down to negative 3, and at 360, we're back up to 2. So let's just label these two so that if you look back on your notes, you know which graph belongs where. So this is y equals the sine of theta minus 2. And then this graph up here was y equals the sine of theta plus 3. Okay. So the one we just graphed, we can see now we have a maximum at negative 1. We have a minimum at negative 3. And again, if I wanted to, I could identify where my axis is. Okay, so our axis is at y equals negative 2. Okay, that's our axis of our curve. So something to notice here, that what we added to the function y equals sine theta, we added a 3. That ended up being our axis of our curve when we transformed the function. Okay, when I transformed the function by subtracting 2, again, my axis of my curve was that minus 2. It was the thing that I transformed it by. So let's take a look at some of the properties of each of these functions now that they're transformed. So y equals the sine of theta plus 3. What's the period? So remember, the period is the length of time it takes for one cycle. So it looks like it's still 360 degrees before we get back to repeating the pattern of that function. So our period is 360 degrees. Our amplitude is that distance from the axis up to the maximum or down to the minimum. So my axis is at 3, the maximum is up to 4. So my amplitude is still 1. Okay, the axis of the curve we've already talked about. That's that horizontal line that cuts the graph in half. So it's y equals 3 for this one. Our domain is still going to be x for all real numbers, because remember, these sinusoidal functions are going to continue on in this pattern infinitely to the right and infinitely to the left. Our range will change a bit because the range is going to be based on our maximum values and our minimum values. So we'd say y for all real numbers, and the lowest value on this graph is 2, less than or equal to y, which will be less than or equal to our maximum, which is 4. Okay, let's take a look at for the other graph where we subtracted 2. So my period is still 360 degrees. That didn't change. Our amplitude is still 1. Our axis now is going to be a negative 2. It's that horizontal line that cuts the graph in half. Our domain remains unchanged, still x for all real numbers. But again, our range is going to be affected by those minimum and maximum values. So the lowest value of y I'm going to see is a -3. This is less than or equal to my y, less than or equal to my maximum, which is at -1. Okay, so just let's make some conclusions about this. For y equals sine of theta plus c, the graph is going to shift in which direction when we are adding, right? So the graph shifts up when c is positive, right? When we had a +3, the whole graph moved up. Whole thing moved up, okay? And the graph shifts down when c is negative. So you can see when we subtracted 2, the whole thing shifted down, all right? And then the one other point I want to make about this is that this vertical shift, so the vertical shift is also the equation of the axis, right? That horizontal line that cuts the graph in half, okay? And the equation of your axis is going to be y equals whatever that c value is that's being added or subtracted to the function. Okay, let's continue looking at another. So now we're going to calculate y equals the cosine of theta, and then we'll talk about, again, what are those key points, and look at what happens when we're subtracting a value from the theta. So we're putting the theta in brackets and we're adding or subtracting a value to it. Okay, so go ahead and pause the video and just fill out this first column here for y equals the cosine of theta for all of those theta values. Okay, so I filled out the table of value, then I also put those values on the graph. Go ahead and pause the video if you need a minute to do that. But what I want to recognize again here is where are those key points. So remember, our key points are our max, our minimum, and our axis. Okay, so we have a maximum at 0, which is 1. So here's our max. And we have a minimum at -1, which occurs at 180. And then again, we hit our max again up at 360. It goes back up to 1. So in this case, we actually hit our maximum twice. But we also have to see where's our equation of where's our axis. So our axis hits at 90 and at 270. So that's another key point. So here's our axis. And here's our axis again at 270. So for the sine curve started at our axis, went up to our minimum, back down to our axis, down to our minimum, back up to our axis. With our cosine starts at max and then works its way down to the axis, minimum, back up to the axis, and back up to the maximum. So those are the different elements of those two functions in terms of where do they start and where do they end. So let's fill out our table of values now for this other function and see what happens. So y equals the cosine of theta minus 45. Okay, so I'm going to start by just crossing out this first box because we don't need to do 0 minus 45. That's going to give us a negative angle. So we'll just start with 45. So for this first one, I just want to show you over here the math of that. So if we had y equals the cosine of theta, in this case our theta is 45, and then we're going to minus 45, then really what we're doing is we're finding y equals the cosine of 0. Well, we know what y equals the cosine of 0 is because we can look in our table of values for that. We know that the cosine of 0 is 1, so that's what's going to go here. Okay, so we'll do one more together and then pause the video and I'll get you guys to do it. So if we're going to do y equals the cosine, and this time we're going to do 90 for our theta minus 45, then we're really doing the cosine of 45, which again, we can look in our table of values for that, and the cosine of 45 is 0.701. So go ahead and fill out this table of values and then plot the new transform graph on your graph above. Okay, so here's our transform graph now on the graph above. So I just plotted this time my key points. So I looked for where my maximum, my minimum, and my axis were, and I plotted those for y equals the cosine of theta minus 45. Okay, and you can see that if we look to see what happened with our original graph, it looked like the whole thing shifted to the right. Okay, and if we wanted to look at how much did it shift, well, it shifted, one box is 30 degrees and then half of another one is 45. So it shifted 45 degrees right. All right, so what can we conclude about this? So for the cosine for y equals the cosine of theta minus 4 to 5, what are the following trig properties? Well, if we evaluated our period again, it's still a 360-degree period. Our amplitude, which is the distance from that axis to the maximum, is still going to be 1. You can see our axis is unchanged from our original function. It's still at y equals 0. Because remember, our axis is that horizontal line that cuts the function in half. So that's right at y equals 0. Our domain is still x for all real numbers. And our range is going to be similar to our base function where it's y for all real numbers. And then it's going to be restricted to the maximum and the minimum. So my minimum is -1, which is less than or equal to y, which is less than or equal to +1. Okay, so seeing what we saw happen though in terms of it shifting it to the right by 45 degrees, we can conclude that if we have a -45 inside of our bracket, that's going to move the function to the right by however much we have in that bracket with the theta. So a -45 is going to move it to the right 45. So then by that reasoning, if we look at our next function, if we have cosine of theta plus 60, that's going to move our function to the left by 60 degrees. So if I look at my original function and I wanted to graph this y equals the cosine of theta plus 60, I'm just going to take each of my points and I'm going to move them 60 degrees. So I'm going to take this point here and I'm going to move it 60 degrees and plot a point. Okay, I'm going to take my next key point, which was at, my key point, which was at 90 degrees, and I'm going to move that 60 degrees to the left. And I'm going to do that for all of those key points on my base function. So 60 degrees. And then finally this point at 360, I'm going to move 60 degrees. Okay, so you can see that for this function, which was y equals the cos of theta plus 60, all right, from our base function, it shifted 60 degrees left. Okay, so let's look at all these features again. So we still have a period of 360 degrees. The amplitude is still 1. Our axis is unchanged, as is our domain and our range. Okay, none of those things were affected by moving it horizontally. So let's summarize what we did find though in terms of what is adding or subtracting something inside the brackets due to the base function. So for y equals cosine of theta minus d, the graph shifts left when d is positive, and the graph is going to shift right when d is negative. So when you have a minus d, it's going to move the base function to the right, and when you have a plus d, it's going to move it to the left. So that is what is the summary of our translations here, the two that we just covered, and then we're going to try a couple. So d, that amount inside of our bracket, represents a phase shift, we call it, which is the same thing as a horizontal shift or horizontal translation. And remember that the opposite direction of the sign dictates what it moves. So minus moves right, plus moves left, which is kind of counterintuitive. C, which is that number being added outside our brackets, is going to represent a vertical shift or a vertical translation. So it's going to slide it up or down. And it's also going to be the equation of our axis, which is at y equals c. So for the next two functions, I'm going to try one together and then I'm going to get you guys to try one. We're going to always try to graph the base function and then apply the transformations to graph the new transform function. So in this equation, we have our cosine function. So I'm going to start by plotting my cosine function. Now, if I want, just so it helps me, I'm going to put those key points that I remember about cosine over here in a table of values. So I know my cosine at 0 starts at its maximum, which is 1. And then it moves every 90 degrees, goes down to its axis. And then at 180 degrees, it goes down to its minimum. At 270, it's back up to its axis at 0. And then at 360, it's up to its maximum. So I'm going to put 1 here and plot those key points. So -1 would be here. Oops. So then at 180, we're going down to -1, 270 we're at 0, and 360 we're back up to 1. Okay, so we're going to take a look at our transformed, and actually let's do 2 cycles. So we're going to repeat that pattern. So from our maximum, 90 degrees later, we go down to our axis, and then 90 degrees from that, we go down to our minimum, then back up to our axis, and then back up to our maximum. Okay, so we're just going to graph that y equals the cosine of theta 2 times. Okay, so now let's look at our transformations that we're doing here. We have a plus 90 inside of our bracket. So remember that is going to be a horizontal shift, and that's going to shift left because the plus tells us it's going left. And then if we have a minus 1, that tells us if we're going to move up or down. And since it's a minus 1, we're going to move down. So let's start with each of our points. We'll grab another color, and we're going to move them left 90 and down 1. So I'm going to start with this point here because the other one is going to take me negative, but you could start with that point too if you had it in the negative. If we wanted to just show that, we'll pretend we can go 90 left and then down 1 somewhere like that. Okay, our next point we're going to go 90 to the left, which will bring us back to our y-axis, and then down 1. Okay, and then our point at 180 negative 1, again we're going to go down 90, or sorry, left 90, down 1. Okay, pause the video and do that for all of the points, and then connect them to make a smooth curve. So this is what our graph should look like when we make this transformation of moving all the points left 90 and then down 1. I also just want to discuss what that's going to look like in a table of values. So when we start doing transformations, then you have options on how you're going to actually do it. So for our x values, right, which is our thetas in this case, we have to look at what we did. So from my first point here, my x value was 0, or sorry, my theta value was 0, yeah. And I moved it left 90. So if I was moving it left 90, I was really subtracting 90 from it. So instead of being 0 now, it's going to be a negative 90. Okay, and then I could perform that operation to all of my thetas. So 90 minus 90 is 0, 180 minus 90 is 90, and so on. Okay, so that's what we were doing to our thetas. We were subtracting 90 from them when we transformed them. What were we doing to our y? Okay, well, this first point was at 1, and I moved it down to 0. So I was, again, subtracting 1 from my y value. So my y value originally was at 1, and I shifted it down to 0. My next y value was at 0. I shifted that down by 1, and so on. Okay, so you could also put in a table of values and then plot those table of value points on a graph. So let's try one more. Okay, so this time we're going to create a table of values and then sketch the graph for the cycle. So what I'd like to do is I'd like to first, let's set up just a table of values for our base function for sine. So we know where those key points are for sine and for cosine. They're at 0, 90, 180, 270, and 360. All right, and remember our sine function starts at 0, works its way up to the maximum, back down to our axis, which is 0, down to the minimum at negative 1, and back to our axis. So if we were to plot that, we could plot our sine curve. It goes 0. Oops, let's give our y-axis some values here again. That's negative 1. Goes up to our maximum, down to our axis, down to our minimum, back up to our axis. Okay, and I'm going to plot 2 cycles. So then again, follow that pattern. We're going to go back up to our max, down to our min, or sorry, down to our axis, down to our min, back up to our axis. Okay, so I'm going to connect all those points to make 2 curves, 2 cycles. Okay, so from there we're going to look at what transformations are happening. So we're doing a minus 45, which means that's going to move the graph to the right 45. Remember, it's the opposite behavior kind of thinking. That if it's a minus 45, we're moving to the right. And if we have a plus 2, we're moving it up as well. So go ahead and pause this video. I'd like you to try this, either by just moving each dot on the graph or set up the table of values. I'll have both solutions when we come back. Okay, so here's the solution for this last problem. All right, my scale was a little off, so pardon that I kind of squished the 2 and the 3 in there. They're a little bit smaller scale compared to where the 1 was. But I took each of my points on the original function, or our base function, which was y equals the sine of theta. Okay, and I moved each one right 45 degrees and then up 2 to get our transform function, which is y equals the sine of theta minus 45 plus 2. Okay, so I transformed each of those points. Or you could put it in a table of values. I could take all my thetas and add 45 to them to get my new theta values. And I could take all my y values and add 2 to them to get all my y values, and then plot those points. Either way will work in order to transform the function when we're dealing with vertical shifts and horizontal shifts. That is it for your note for today.